So Uber built an AI copilot, and it's already saved 13,000 engineering hours in its first year of production. So in this video, let's break down Uber's deployment, starting with the business use case, going into the deployment architecture, and then obviously ending with the business value that they obtained in the end. And covering all of this will help us learn the best practices and lessons for our own AI deployments going forward. Now, for those who are new here, I've built dozens of AI implementations. I've done it for some of the world's largest companies, and they do look very similar to what we're going to discuss in Uber's architecture today. Now we're going to cover today a 0 to 1 deployment. So this will be the initial deployment that Uber actually did. But going forward, we're going to look at the improvements that they made over time to get additional ROI and additional value from their use case. But that will be a separate video going forward. So with that, let's go into Uber's Copilot and let's start with the problem that they're actually trying to solve. On-call operations is crucial to ensure that Uber's services are running successfully, and Uber's engineering teams support 45,000 questions a month. And so what typically happens is today a user is going to post a question to a Slack channel for an engineer to actually pick up. And this often goes through multiple rounds of back and forth between the end user and the on-call engineer to understand the problem and really triage it. But many of these questions could actually be resolved by looking at existing documentation. It was just very difficult to actually find because it was scattered through multiple different source systems. And so as a result, unfortunately, the end users are going to ask the same questions repeatedly over and over again, and on-call engineers have to triage the same issues as well. And then obviously more questions, more wait times, and longer wait times going forward. So this is where Uber decided to build Genie, which is their on-call AI copilot. So how did Uber actually build out and design this copilot solution? So for their use case, they chose RAG, or retrieval augmented generation. And this was their first design decision. They could have went for a fine-tuned LLM, but in this case, they would have needed to have a lot of high-quality sample data, and they would have had to have compute resources that consistently updated over time. They even talk about this directly in their post. They say, and I quote, "RAG doesn't require any diverse examples to begin with, and this reduced the time to market for the Copilot launch." Now this matches my experience, but also a broader industry trend as well. According to Andreessen Horowitz, most companies are actually shifting away from fine-tuning because they're not obtaining an ROI from it. And this is mainly because the model capabilities out of the box are just so much better than they were before. So here Uber's choosing RAG for speed and flexibility, and then also down the line and in future implementations, they create an agentic solution as well. We'll cover that in a separate video. Now here at a high level, this is Uber's Copilot architecture, starting with data. Remember, they're a larger company, so they have full ETL pipelines that they need to be consistently pulling data in at scale. Then there is the actual generation piece itself. They have their own service. And then last but not least, the user interaction. In this case, they're looking through Slack channels. But let's go into the details of this, starting with the data. So production systems need ETL to ensure that the data is consistently up to date. So here's the high-level architectural flow, and it first starts with the data prepping stage. This is where first the pipeline is going to fetch a bunch of different data sources. This is from their engineering wikis, that is their actual internal Uber wiki itself. They call it EngWiki. There's some other data sources as well they pull in and actually fetch consistently. And this outputs a data frame where they're going to have the URL, the content that they pulled, and then also some metadata attached to it as well. Now the second piece is the embedding creation. Now, because it's RAG, we have to chunk and we have to embed it. So here they're going to chunk via LangChain and they're embedding via OpenAI embedding model. Now, next they have a vector pusher. I'm not going to go into the details of this, but they essentially have a couple of jobs where they push it into their TerraBlob. And this is Uber's internal blob storage. And then lastly, on daily intervals, the vector database is going to fetch the latest embeddings, and then from there, it's ready for retrieval for the downstream RAG pipeline. Now, there's a lot of design decisions in here that are specific to Uber's requirements for scale. But what can we take away from just the data side alone right now for our direct implementations? Now, first here is choosing the data carefully. Now, Uber has a lot of data that they couldn't actually expose via Slack channels due to security reasons. So they started with data that is still valuable, but everybody can access. Now, security aside, there's also a frequency that they need to pull the data from consistently. Now for Uber's case, they're updating the data daily, and you're seeing this in various parts of the pipeline. Now I will say, just in a lot of my use cases, you're not going to pull everything daily all the time. Some data sources require weekly ingestion, daily ingestion, hourly ingestion, right? So it's very dependent when you scope out these use cases of what is the ingestion requirements for each data source. Now another detail here is the additional metadata that they added during the data prep stage. Now this does go into data modeling a little bit later, but having additional metadata can help you improve retrieval going forward. And I'll use a quick example from my own personal deployments. In a similar Copilot type project that I ran, we need to extract information directly from the documents itself. In this example I'm talking about is actually the name of the document. Now, the file name was a code, but people don't search via codes, they search via the names. And so we had to actually go into the document, extract that metadata in there as the name, and then that would be used to improve retrieval going forward, not only for the AI, but also for end users if they're searching for it. Now, that's just a quick example, but when we go through these projects, additional metadata is typically helpful for additional retrieval capabilities. So now the data is set up, let's actually go into the AI-generated content that they were creating. So when a user asks a question in Slack, it gets taken care of by Uber's backend service called Knowledge Service. And this converts the user question into embedding, and then from there, it fetches the relevant chunks from the vector database. Now, this is typical RAG, but to reduce hallucinations, they need to make some changes to the way they sent the prompts over to the LLM to improve the accuracy. So for retrieval from the vector database, they added a subcontext and also a URL to cite sources. And they prompted the LLM to ensure that it was always citing its sources. And so this means that every single question should include a source citation that end users can go and validate. And obviously without this, end users will not be trusting it and it would obviously hurt adoption going forward. Now, to be honest, this is pretty basic, but I do this on all of my projects, no matter what, honestly, without fail. And the reason why is because we have to assume the AI is not going to be 100% accurate. But an additional nuance here is that even if the AI is wrong, providing source citation is still valuable in terms of economic value for the end users. And what I mean by this is, let's just say the AI does get it wrong, or maybe it's partially correct. Well, at the end of the day, and especially for this use case, the end users can still look at those source citations, get the information anyways, and then that obviously reduces the on-call engineers having to step in. So at the end of the day, you're still getting the value added. And this is something that I call AI assisted, where the AI either partially gets it right or wrong, but it's still providing source information that is still economically beneficial for the end user. And this leads me to my final section on architecture, which is the end user interaction. Now, as I mentioned, the Uber Copilot system is built into their Slack system. And you can also provide via Slack 4 different feedback options. First is resolved, so the answer is completely resolved the issue. Helpful, where the answer partially helped, but the user still needs some help. Not helpful, the response is completely wrong or not relevant. And then not relevant, as the user needs help from somebody on call and the AI can't assist. As an example for this, it could be a code review or something along those lines, where the AI couldn't do it anyways. Now, when a user leaves feedback, this is actually captured, and then they can visualize it in some metrics going forward. And this is how Uber knows that they have a 48.9% helpfulness rate. Now, Uber also added a new interaction mode for them, where end users can ask questions, ask follow-up questions, mark things as resolved, or even escalate as needed to a human. And so this changes the flow, where now on-call engineers only help when it's getting escalated. So there's a few things I want to point out here. The first is that they actually implemented feedback mechanisms into their existing Slack system from day one. So they already planned that this is the feedback they're going to have. And this is important because after you go into production, this continuous feedback helps you improve over time. And the second thing I want to bring up here is making sure that we're meeting users where they're at. So here, they created a Copilot on Slack. They didn't create a separate application where they had to migrate end users over. And this ensures that there's less friction for adoption going forward. And then obviously, and we'll get into the next section, improving the economic value as well. Now, for those who are implementing AI use cases, just like me, you're going to scope an AI use case, you're going to build it, you're going to deploy it. But this whole entire time, we have to think about the economic value that is provided to the business in this case. And so for the results for the Copilot launch, these are kind of the raw statistics here. 154 Slack channels, 70,000 questions answered, 48.9% helpfulness rate, and this equated to 13,000 engineering hours saved. Now, Uber doesn't really detail how they came to this number and obviously the economic value of this, but this is how I would do it if I was running this project. You have 70,000 questions, you have 48.9%, which is roughly 34,000 successful questions resolved by the AI. If each question would have taken an engineer 20 to 30 minutes to resolve it, that would be approximately 11,000 to 17,000 hours saved, which is kind of our ballpark here in the 13,000 range. Obviously, we multiply by salaries, and then that's the economic value gained. However, that's not really the whole thing. What about the cost to run it? Now, Uber did implement a cost tracking system inside of it. And so they'd be able to track the spending per channel and also have an audit log for it. And so the calculation would look more like the 13,000 times the salaries of the employees minus the total cost to run here. And I want to stress this because this is really important for a couple of different reasons. First is identifying important use cases to start. So what is the ROI required when we do this use case? And then when we build it, you're going to need to consistently justify to upper management on, yes, this was a valuable use case. And then going forward, these additional improvements, if we improve the helpfulness rate by 5 or 10%, this is the additional economic value going forward. And then from here, this is still a viable project to continue funding for. Now, this is not a static deployment, right? The initial economic value of it is going to change over time, especially when we make improvements. And this is where the roadmap comes in to ensure that we continuously improve our system. So Uber did some interesting things here. They actually created 2 systems to improve the quality. So first, Uber set up an LLM as a judge to run consistent evaluations over time. And so these evaluations actually help triage individual issues and improve each of the RAG components over time. Second is actually evaluating the source material, in this case, the documents itself. And here a direct quote from the article: if the quality of the documentation is poor, no matter how good the LLM performs, there's no way to have good performance. So here, after the data is scraped, the LLM as a judge gives it a score, and then it also provides information on how to improve the document quality. And so for this use case, it's pretty straightforward, as any improvement towards helpfulness rate is going to improve your bottom line economic value. And so as you can see, these 2 improvements will improve that helpfulness rate. So this is the overall solution. I want to actually just go through what are the highlights that we should really be taking away to ensure that we can have better deployments going forward. The first one was speed to value. In this case, they directly discuss in the article that they chose RAG because it was faster. And so in this case, if you go faster, you can get value faster. Next, ensuring the data quality is high, and they directly said this too. If the document quality is poor, the LLM inference isn't going to be good. Now, data quality obviously important, but making sure that we're getting the latest and updated pieces as well, which came from their large ETL pipeline. Next is ease of user adoption. Like I mentioned, they met the end users where they were at. They were already on Slack, so they built a copilot for Slack. But they also, when there was inference, the LLM made sure that it was always outputting the source citations for end users to validate as well. And last but not least is the measurement from day one, essentially, right when they started. They had built-in feedback to make sure they were tracking the helpfulness. They also had, measurements in terms of the document quality as well. And they even had the tracking for costs, which is important for the economic value on your bottom line. Now here we discuss the first implementation. This is the 0 to 1 implementation that Uber did for their Copilot. But after you do 0 to 1, you don't just drop and leave, you need to go from 1 to 100. And that includes making improvements and also scaling out across the organization. And so in a future video, I'm going to go through this exact thing of how Uber made improvements and then scaled it across the company. And then ultimately what we can learn from their deployment. So anyways, thank you so much, and I'll see you in the next one.